Hello and welcome to this lecture series on communication systems. My name is Saurabh Mani Tripathi. I am an assistant professor at IIT Kanpur, and in this lecture we will be basically studying the electronic communication system. But before we go into detail of electronic communication system, let us first try to understand what do we mean by communication. So, in the simplest form, communication is the act of transmission of information. So, in the simplest form I can write that communication, this is basically the act of information transmission. Now, every living entity does this. For example, you can think of a little boy or a girl, infant age. So, what this person does when it feels hungry or any pain. So, the little baby starts crying. Does not matter if a person is feeling hungry or is in pain or simply missing his or her mother. So, this act of crying is basically the act of transmission of information. So, the first example that we can consider is that of crying baby. So, whenever the baby is in pain or is hungry or maybe simply missing his or her mother, the baby starts crying. And if we can listen to this cry, we can rush to the baby. But what if we are not in close proximity of the crying baby? What if we are, let us say, hundreds of meters away? We cannot simply listen to the baby. So, in that case, we need a messenger who can transfer the information from the baby to us. That is one thing, that we need to have a messenger. And the second thing is that the messenger must understand the language of baby, and we should also, we who are at the receiving end, should also understand the language of the baby. So, for this information to successfully pass from the baby to us, two essential requirements are: number one, let us use a different color. Number one is that there should be a messenger if the baby is far away from us, and number two requirement is that the messenger and us who are at receiving end should understand language of baby. So, the basic requirements are that we need to have a messenger and we must have a common language. Now, let us take another example, example number 2. Let us think about birds. So, what if these birds, for example crows or sparrow, they see a cat in very proximity. So, these birds starts chirping, they starts crying, creating lots of very huge sound, very large noise, and this, by this act they want to transmit the information that there is a cat nearby. So, once again we see that it does not matter what kind of living creature we are talking about, all the living creatures some point of time in their life must communicate to each other. So, second example is that of cat and birds. So, whenever birds see a cat nearby, they start creating huge noise, and by this noise, by the act of creating noise, they are passing on the information that there is danger nearby. So, in both of these examples, we see that for the communication there is one source of information, which in the case of crying baby is maybe the pain or the hunger, and for the cat and bird case it is the danger nearby bird. So, there need to be one source of information. There also need to be at least one receiver of information, and there need to be at least one channel through which the information is passed. For example, what if the baby is crying, let us say, in vacuum? We know for sound to travel, for sound to propagate, a medium is necessary. So, if the baby is crying in vacuum, we will not be able to hear the voice. Similarly, if the birds are chirping in free space, we will not be able to hear the chirp. So, we need to have a channel through which this information can propagate. Now, the second thing is, what if, as we have already discussed, what if the crying baby is far away from the source? So, in that case the baby cannot simply come to us to tell that he or she is in trouble. So, we must have a messenger. Similarly, if the baby has grown up, he may cry at a louder pace, at a louder voice, and we can also listen to that. But what if he is miles away? So, he has only two possibilities: either he himself comes to us to transfer the information, or he can employ someone who can come to us on his or her behalf to transfer the information. So, when the source of the information and the receiver of information are far away, we need to have a carrier in between. So, a carrier of information is needed if the source of information and receiver of information are far away. In modern electronic communication, if we want to draw a block diagram of different components, we can include all these three essential components, and we have a source of information. This will then be carried by a carrier, and this will then be received at receiver of information. So, in block diagram I can have a transmitter which will transmit the information. For example, in the case of crying baby, the baby is the source of information. His mouth from which he or she is crying, that is the transmitter. So, we need to have a transmitter, and then through this transmitter this information will then go to a channel which in the case of crying baby is air. So, this information must pass through a carrier and then it will come at a receiver, which in the case of crying baby is our ear. So, from our ear we are receiving the cry. So, these are three essential building blocks, but before and after these three we also need to have some other blocks. For example, the transmitter, the mouth itself cannot transmit the information until and unless it has some information. So, we must also have a source of information from which this information will be transmitted, and we also need to have a receiver of information. So, from source of information it goes to the transmitter, from transmitter it is passed through a channel, through channel it goes to receiver, and from receiver finally it is available for receiver of information. Now, in the channel mostly a lot of unwanted information is also added, and we call that unwanted information as noise. So, in this lecture we will study step by step about, first we will study about the transmitter, then about the channel, and then about the receiver. We will basically study the underlying physics behind these. So, let us first try to understand what is a transmitter. Now, please keep in mind that the transmitter as well as the channel and the receiver, these are not a single entities, they themselves are systems. So, the transmitter itself is not a single entity, it is a combination of many different entities, and by itself it is a system. So, in transmitter in electronic communication we first of all need to convert the information into electrical signals. Now, our information, the information that we have can have many different forms. The information that we want to communicate may have a form of voice, we may want to send voice, or we may want to send some picture, or we may want to send a video or some other data file. So, these are some example of the kind of information that we may want to transmit. Now, out of these, the first information that was electronically transmitted was in fact kind of in the form of dots and dashes, and that was basically the telegram. So, we will not going to study that, we will rather start our discussion about the transmission of voice. As we know, voice, the sound voice has a frequency range that our ear can understand, that our ear can receive, and for humans the range of this voice signal, the frequency of that ranges from 20 to 20,000 hertz. This is the frequency range that our ear can listen. That is the range that our ear can receive and process, our brain can process. Now, if we want to send this information electronically, we first of all need to convert from voice, from sound wave, which is a mechanical wave, to an electrical signal. So, how exactly we do that? For example, here I am speaking and in the room everybody can listen the voice itself, which is a mechanical wave, but if you want to listen it to a far distance away, first of all before I transmit it, I need to convert this into electrical signal. Now, why electrical signal, why not any other kind of signal? The advantage of converting this into electrical signal is that the electrical signals can be transmitted at a very high speed. The speed can be as fast as the speed of light itself, that is kind of 3 into 10 to the power 8 meters per second. So, that is the biggest advantage of using electronic communication system. You can have the conversation in real time, you can transfer the data, you can transfer the video or the picture in real time, and that is why we want to understand this electronic communication. So, first thing that we want to do is whatever information we have, be it in the form of voice, picture, video or data file, we want to convert this into electrical signals. How exactly we do that? For voice, we use a transducer in the form of a microphone. So, for all of these different kinds of information, first thing that we need is to convert it into electronic form. The first requirement is convert the information in electrical signal or electronic form, and that is done by using a device that is called transducer. Now, this transducer by definition can be anything that converts an input information in the form of pressure or vibration or anything into electric signals. So, this takes input and this converts the signal into electric signal. Now, your signal may be pressure or temperature or vibration, can be anything. So, after the transducer we start getting electrical signal. The same thing, the variation of pressure or the variation of temperature or the variation of vibration in terms of time is converted into a similar variation of electrical signal. Now, electrical signal can be in the form of current or in the form of voltage. So, this can be either current or it can be voltage. So, it takes the input in the form of pressure, temperature, vibration or other things and converts into a similar variation of current or voltage. Now, this current variation or the voltage variation is then sent to the channel, and from channel it is sent to the receiver. Now, what really we do if we want to transmit our voice to a far away distance, until unless we have a channel in between in the form of wire or optical fiber, we generally do not send the electrical signal as such. We do not send the output of the transducer as such to the communication channel, and there is a reason. Why we do not send it as such is because of the following fact. Let us first consider that we want to send a voice signal, and the voice signal may have a frequency, as we know, from 20 to 20,000 hertz. Let us suppose that we want to send the information that is at 3000 hertz. Let us suppose that the voice that I want to send has a frequency of 3000 hertz. Now, what will be the wavelength of this frequency? Once it is converted to electrical signal, the frequency is related with the speed at which it is being transmitted through this relation. We know, for that matter, speed is given by frequency times wavelength. Since the speed is equal to, I will write now the symbols. So, speed is v is equal to frequency, that is nu, times wavelength, that is given by lambda. So, let me write it, this is wavelength, this is frequency, and this is speed. Now, we know that electrical signals travel as fast as the speed of light. So, we know that v is going to be the speed of light, that is 3 into 10 raised power 8 meters per second. The frequency, as I have already said, let us say that we want to send a frequency of 3000 hertz. So, what should be the wavelength of this signal? So, from this equation we can calculate that 3 into 10 raised power 8 is equal to 3 into 10 raised power 3 into wavelength. So, lambda comes out to be equal to, precisely equal to 10 raised power 5 meter. That is equal to 100 kilometer. Now, if we want to send this signal through air, we need to have an antenna. We need to have an antenna from which this signal can be transmitted. And generally, for the simplest antenna, the dimension of antenna should be equal to a quarter of a wavelength. The requirement for a simple antenna is that the dimension of antenna should be equal to 1/4 of the wavelength that you want to transmit. Now, if we go by our calculation, the length of the antenna that is needed if you want to transmit a voice of a frequency 3000 hertz, the length of antenna will come out to be equal to 100 divided by 4 kilometer, that is equal to 25 kilometer. So, if you want to send your voice of 3 kilohertz frequency as such, without changing it, without of course, it has been converted to electrical signal, but if you want to transmit it as such, the length of the antenna should be equal to 25 kilometer. Now, there are very serious practical implications of having this big antenna. You cannot simply have this big antenna. So, what we do is we try to avoid sending the voice signal directly converted into electrical signal as such. That is one of the limitation why we cannot send the voice signal as such. Second requirement is the energy. The second requirement, this was the first requirement, the second requirement is typically the power that is radiated by antenna is proportional to length divided by wavelength and everything squared. So, this is the general requirement. So, if the wavelength is very big, for example, in our case wavelength was 100 kilometer. For such a big wavelength, the power that will be radiated will be very small. For example, if we go by this calculation that we have just now written, if we fix the length of the antenna, let us suppose that I am fixing the length of antenna as capital L, and I have two different wavelengths which correspond to two different frequencies. Let us say I have a wavelength lambda 1 and which is much larger than a second wavelength, that is lambda 2. So, how much power will be radiated at these two wavelengths? We see that since power radiated is proportional to L by lambda squared, if since lambda 1 is much larger than lambda 2, we see that power radiated at lambda 2 is much larger than power radiated at lambda 1, and keep in mind that same antenna has been used. So, from the second condition also we see that smaller wavelength, we know that means higher frequency. So, from this conclusion we see that higher frequencies are transmitted with more energy. So, if we are transmitting the information, and if at the source from which, at the transmitter from where it is being transmitted, the energy itself is very small, it will not propagate at a far distance. So, for these two reasons, generally higher frequency signals are preferred for transmission. So, if the frequency is high, wavelength will be very small, and the requirement of the dimension of antenna will also be very small, that is first thing. And second thing is, higher frequency will have higher energy. So, you will need repeater or amplifier at a large distance from the source at which the information is being transmitted. So, we see that the frequency of transmitted signal should be high because of two reasons. The first reason is because at high frequencies small antennas will work fine, and the second thing is that signal that is transmitted will have high energy. Now, there is also a third requirement why we cannot transmit audio signal at a frequency lying between 20 to 20 kilohertz, and that requirement is, let us suppose that we want to transmit audio signal from many different sources. Let us suppose that there are hundreds of people who are talking, and we want to transmit all these voice signals to different places. So, if everybody is talking with their own frequency, before that, one important thing that you need to understand is that when we speak, we do not speak at a fixed frequency. We have a range of frequency. Even the word that I am speaking right now does not have one given frequency. There is a range of frequency. Second thing that you also need to keep in mind is, although our ear can hear frequencies ranging from 20 to 20 kilohertz, the frequency that we speak, the word that we are speaking has a limited range of frequency. Generally, the range of frequency that we speak lies between 300 hertz to 3100 hertz. This is the frequency of common voice. So, there is a huge difference between these two. Typically, this is of the order of the exact value is 2800 hertz. So, that is the frequency range of our voice, and this range is also known as bandwidth of voice, that is bandwidth of human voice. I need to write human here. Now, if let us suppose we have hundreds of people who are speaking, and let us suppose at least 2 or 3 of them are speaking in the same band of frequencies, and if you want to transmit the electrical signal, that is right away converted from voice signal as such, at the receiver end it will be very difficult, practically impossible to distinguish between different voices, because many different voices are transmitted over the same band. So, it becomes practically impossible to distinguish who was speaking what and to whom that person was speaking. So, for this reason also we cannot simply transmit the signal, voice signal converted to electrical signal as such. So, what we generally do is we try to encode another electrical signal which is of very high frequency. So, we try to encode this very high frequency signal with our electrical signal that is converted right away from the voice. So, what we do is we modulate a carrier. Remember, when a person or a boy or girl who was far away from where you are, and if that person wanted to communicate to you, a medium, a carrier was needed. A carrier was needed who can carry the information to you. So, similarly, if I want to transmit my voice, I need to increase its frequency, but we know that our frequency is limited, the voice frequency is limited. So, what we do is we take a carrier and we modulate this carrier. Now, what do we mean by modulation? What is modulation? So, in simplest term, modulation is mixing of information signal with a carrier signal. Now, we know that a carrier signal can be expressed mathematically in a sinusoidal form, and let us say that I have a signal which I am going to see as E. So, I can write this in the sinusoidal form like E naught sine of omega t. So, this electric field which is given by E is varying with time. The first part of this equation, this E naught, we know that this is amplitude, and this part which is in the argument of sine is known as phase. And in the phase itself, the first part omega is frequency, that is angular frequency, that is angular frequency. And we can also write the same equation as E naught sine of omega t plus another phase factor phi. So, here phi is an additional phase. This phi is additional phase. So, if I want to modulate the carrier signal with my information signal, I can either change the amplitude of the carrier signal, or I can change its frequency, or I can also change its phase in accordance with that of the information signal. So, if I change the amplitude of the carrier signal in accordance with the information signal, the modified signal will be known as amplitude modulated. So, if the amplitude of the carrier is modified in accordance with the information signal, this information signal is also known as modulating signal. This is known as amplitude modulation. Second thing is that if the frequency of the carrier is modified in accordance with the information signal, then this is known as frequency modulation. And finally, if the phase of the carrier is modified in accordance with the information signal, this is known as phase modulation. Now, let us suppose that the frequency of your carrier signal is of the order of megahertz. Let us suppose that the frequency of carrier signal is of the order of, let us say, megahertz, and let us say this is 1 megahertz. 1 megahertz means 10 to the power 6 hertz. What will be the wavelength of this wave? We know that we can calculate the wavelength using the same relation, that speed is equal to frequency times wavelength. Speed once again is 3 into 10 to the power 8 meter per second. Frequency has become 10 to the power 6 hertz, and wavelength, let us say, is lambda. So, lambda will be equal to 300 meter, and therefore, the dimension of antenna will be lambda by 4, and that will be equal to 75 meter. Now, compare this 75 meter to 25 kilometers. So, this antenna can be easily made. So, we see that if we are using a carrier signal which has a very high frequency, the dimension of the antenna is drastically reduced. Now, let us focus on the first thing of the modulation, which is amplitude modulation. So, as I said, in amplitude modulation, the amplitude of carrier wave or carrier signal will be modified in accordance with your information signal. Let us see what this does. So, if I express the carrier wave by an equation that C is equal to C naught sine of omega c t, this is the electric field of the carrier wave, C naught is the amplitude, and omega c is the angular frequency of the carrier wave. So, C naught is amplitude and omega c is angular frequency of carrier wave. And if similarly I express the modulating wave or information signal if I express this in terms of m is equal to m naught sine of omega mt, as per the definition of amplitude modulation, the amplitude of carrier wave is to be modified in accordance with the modulating wave. Let us go to the next page. So, the equation of modulated, that is, now the amplitude of carrier wave is now modified. So, the equation of this modulated wave will be, so I can write C of modulated as whatever amplitude it had originally plus m is my modulating wave, sine of omega ct. You see, omega c has not changed, the carrier frequency does not change, the amplitude has changed. Now, let us expand this. So, I can write C naught plus m naught sine of omega mt, this is the amplitude part, and sine of omega ct. Let us further expand this. So, I will write this as sine omega ct plus m naught sine omega ct sine omega mt. Further simplification, sine of omega ct plus I can write here C naught into m naught divided by C naught, sine of omega ct sine of omega mt. Now, this quantity m naught divided by C naught is known as modulation index. This is known as modulation index. It tells you how much the amplitude of the carrier wave has been changed. This is the measure of that change. So, let us go to the next page. And the equation of modulated wave was, let me go back. Yes, so the equation was Cm, this was Cm, and this was equal to C naught sine of omega ct plus C naught, and modulation index I am going to represent by mu, sine of omega ct sine of omega mt, where mu is equal to m naught divided by C naught, the ratio of amplitude of modulating wave with respect to the carrier wave. Now, here we can use the trigonometric relation that sine A sine B is equal to half cos of A minus B minus cos of A plus B. We use this simple relation and we will get Cm being equal to C naught sine of omega ct plus C naught mu divided by 2 cos of omega c minus omega m t minus C naught mu divided by 2 cos of omega c plus omega m t. This is the final expression of the electric field of the modulated wave. This is electric field of amplitude modulated carrier wave. Now, have a look on this equation. What we see is this amplitude modulated wave now has 3 different frequencies. First one is omega c, that was the carrier frequency, the frequency of the carrier wave. Second one is omega c minus omega m, that is slightly less than the carrier frequency, and the third one is omega c plus omega m, that is slightly larger than the carrier frequency. So, the amplitude modulated wave will be superposition of 3 different waves, one propagating with frequency omega c, the other one propagating with frequency omega c minus omega m, and the third one with the frequency omega c plus omega m. So, if I draw this, if I draw frequency on the horizontal axis and the field amplitude on vertical axis, I will have one frequency omega c, that is the carrier frequency, slightly larger frequency, that will be omega c plus omega m, and slightly less frequency omega c minus omega m. So, the transmitted wave will have 3 frequencies. These 2 frequencies, omega c minus omega m and omega c plus omega m, are known as side bands. So, these 2 are known as side bands. The lower frequency is known as lower side band and the upper frequency is known as higher side band. So, originally the carrier signal had a frequency omega c, whereas now the wave that is being that has been amplitude modulated will have a frequency that will range, the range of frequency of amplitude modulated wave will be from omega c plus omega m to omega c minus omega m. So, the range will be the difference of these 2 and that will be 2 omega m. So, the amplitude modulated wave will be centered at omega c, but it will have a band of bandwidth 2 omega m. Now, how does this amplitude modulated wave look like? Let us draw that pictorially and see how does this wave look like. So, I am going to draw amplitude here, time here, this is time axis and this is amplitude axis. So, originally my voice signal had a low frequency. So, I am going to draw it like a sinusoidal pulse of some low frequency. This is my original signal. Then the carrier wave will have little larger frequency. This is carrier wave and it will have a larger frequency. So, I am going to draw it with lots of maxima and minima. So, this is my carrier wave. So, this is this big. Now, since the amplitude of your carrier signal is to be modulated as per the input signal, so your modulated wave will look like this. Its amplitude will change in accordance with the input signal. So, let me draw a line first. This will guide me what portion of the wave lies in upper or lower part of vertical axis. So, my amplitude modulated wave will look like this. Like this. So, it will have an envelope of the original voice signal, but the frequency of the wave will remain as such as that of the carrier frequency. So, this one is amplitude modulated wave. This is time axis and this is amplitude. Now, let us try to see what happens if the amplitude of carrier wave is of the order of your original signal. And the second case that we will study is, we will study three cases basically. What happens if the carrier wave has the amplitude equal to that of the original signal, and what if the carrier wave has higher or lower amplitude than as compared to that of the original signal. So, first case, let me draw, is when amplitude of carrier wave is larger than modulating wave. To have a better understanding, let us say that amplitude of modulating wave is half of that of amplitude of carrier wave. So, this is the amplitude of modulating wave is equal to half of amplitude of carrier wave. In this case, modulation index will be equal to, that will be AM divided by AC, and that will be equal to half or 0.5. Now, pictorially this will look like this. So, this point is 1, that is the amplitude of my carrier wave. This point is plus and minus half, this is 1.5 and this is 0.5. Similarly, on the negative side, this is minus 1, this is minus 0.5, this is plus minus 1.5. So, we know that frequency is not going to change of the carrier wave. So, it will start like this, it will go to a maximum value. So, there is a small error, let me redraw it. So, it will start from here, it will be like this, it will go to a maximum value and then it will start decreasing again. And then again it will go to other direction, then again like this, this will come here and then again it will start increasing. The point is that its maximum point that will be attained by the maximum amplitude that will be attained by this wave will be 1.5, and the minimum will be close to 0.5. So, it will be like this. Similarly, on the other side also, this is the amplitude modulated wave, and we see that the modulated wave carries the original signal in a very nice form. This is the case when mu, that was the modulation index, was equal to half or 0.5. So, amplitude of modulating wave was less than amplitude of carrier wave. Let us now consider a case when modulation index is 3/2 or equal to 1.5. That means amplitude of modulating wave is larger than amplitude of carrier wave. Now, in this case, if I draw the same figure here, this is 1, let us say this is the amplitude of carrier wave, and the amplitude of modulating wave will be 1.5. So, it will become 2.5 here, and this is minus 0.5, this is minus 1, and let us say here this is minus 2.5, this is plus 0.5. So, my modulating wave itself will range from here to here like this, and in negative direction it will range from here to here like this. And so we see that when the amplitude of modulating wave is smaller than the amplitude of carrier wave, the modulated wave looks very nice and it contains all the information of the modulating wave. So, in the next lecture we will basically study what happens if the modulation index is larger than 1 or when the amplitude of modulating wave is larger than the carrier wave, and we will see that some information is lost in that case. Thank you very much.